Now we're going to take a couple minutes and talk about oxidation and reduction reactions. Previously, we have seen reactions in which we just have the transfer of electrons occurring in the reaction. Let's take, for example, iron reacting with copper sulfate. It's going to form iron 2 sulfate and copper solid. In this particular case, if we look at each of the metal, what's going on is iron is giving up 2 of its electrons to become Fe2+, and copper is gaining those 2 electrons to become copper 0. The sulfate doesn't change what's going on, so that's going to remain unchanged during the reaction. But when we have this type of reaction, we have what we call an oxidation and reduction reaction. So in order to talk about these reactions, we need to talk about the oxidation states of atoms. Typically, we refer to the oxidation state as the oxidation number, which is going to be the actual charge on the atom if it exists as a monatomic ion. Well, let's take this example of magnesium reacting with oxygen to form magnesium oxide. The first rule is that all elements are always going to have a 0 charge. It doesn't matter if it's a diatomic element or a monatomic element or a polyatomic element. As long as it's an element and it isn't bonded to anything else, it will have 0 charge. So magnesium in this example will be a 0 charge, and we indicate that by putting a 0 above the magnesium. Also, oxygen, O2, will have a 0 charge, so we indicate that as well. The next rule is that molecules must sum their charge to 0. Typically, we will get the charge of the atoms in a molecule from the periodic table. Magnesium is an alkaline earth metal, so that would have a 2+ charge. Oxygen, as oxide, would have a 2- charge from its location on the periodic table. The only wrench that we have to deal with is when we have polyatomic ions. The components in a polyatomic ion must sum to the ion charge. So let's look at the oxidation numbers of polyatomic ions in more depth. Let's take sulfate, SO4 2-. Well, we're going to have an overall 2- charge in our compound, in our ion. And each oxygen is going to be an O2-. That means we're going to have 2- charge times 4 atoms, which is going to give us an 8- charge. In order to have the compound have an overall 2- charge, the sulfur then has to take on a 6+ charge to counteract the excess electrical charge from the oxygens. You can do this finding the individual oxidation states for almost every atom in a polyatomic ion. Most of the time, though, these have to be done such that we can see if the polyatomic ions, if they change, let's say from sulfate, SO4 2-, to sulfite, SO3 2-, we would see that the sulfur is changing its oxidation state from 6+ to 4+, going from sulfate to sulfite. So keep that in mind when you're trying to balance oxidation and reduction reactions, because we have to take into account every type of charge change that occurs in our molecules. So let's go back and look at this iron and copper 2+ goes to iron 2+ and copper equation. We take a look at the iron, and that's going to give up 2 of its electrons. It's going to have a 2- on the electrons, so we're going to have a 2+ charge on the iron itself. Well, when we want to classify that, Anytime we lose electrons, we're undergoing what we call oxidation. The exact opposite occurs with the copper. Copper 2 plus gains 2 electrons to get a zero charge on the copper. This is considered a reduction. So anytime you gain electrons, you undergo a reduction. We can use a mnemonic device to remind ourselves of this relationship. Leo, the lion, goes grr. Leo, LEO, stands for losing electrons is oxidation. So that way our electrons will be to the right of our arrow if we separate out for our particular elements that are changing places. GER, stands for gaining electrons is reduction. Electrons would be to the left of the arrow. There is also another mnemonic device, oil rig, where oil, oxidation is loss, and rig, reduction is gain, can be used if you think that one would help you better. In either case, we need to identify the species that's undergoing oxidation and reduction so that we can determine which one is gaining electrons and losing electrons in our oxidation reduction reactions. Remember, you have to categorize the oxidation state of every atom in a compound to make sure that you have an oxidation and reduction going on. One of the other issues that we have when dealing with oxidation and reduction reagents is what I call a tongue twister. We tend to use the word agents when we talk about either reactants doing a particular action on another reactant. In this particular case, we can have oxidizing agents. These are species that oxidize another species. It itself undergoes reduction. So every time we have a compound that undergoes reduction, it is an oxidizing agent. Reducing agents are the exact opposite. Those are species that reduce another species. They, in themselves, undergo oxidation. So whatever undergoes oxidation is a reducing agent, and anything that undergoes reduction is an oxidizing agent. Alright, so let's practice this on one more equation. If I take zinc solid and react it with copper 2 chloride, I'll get zinc chloride aqueous and copper solid out of the reaction. Well, the chloride is not changing its oxidation numbers. So let's simplify this. Zinc will have an oxidation state of 0. Copper on the left will have an oxidation state of 2 plus. To the right of the arrow, we'll have zinc 2 plus and copper 0. Here, the zinc loses 2 electrons, so it undergoes oxidation. The copper then gains those 2 electrons to undergo reduction. If we look at agents, because the zinc underwent oxidation, it is a reducing agent. It is causing the copper to be reduced. Copper, because it is gaining its electrons, underwent reduction, but it had to get those electrons from somewhere. So it is an oxidizing agent because it forced the zinc to give up its electrons. In class, we will practice a few more of these by just identifying oxidation and reduction reactions and looking at the oxidation numbers of compounds to determine if an oxidation or reduction has actually occurred.